Good morning, everybody. I hope everybody's doing well. Give me a moment while I just fix one thing here that's bothering me. That is incredibly dark, but that'll work. All right. A couple things I want to mention before we get started. Just logging into my laptop here so that I can have my digital writing screen ready to go. If you have logged into my Open Math or my Open Math website since last night, you probably have noticed that there is now a link to, let me share my screen. There we go, and I'll zoom in there as well. All right. So at the very top of our My Open Math site is an Integration B study guide. We have the Integration B coming up. That is on the 30th. So it's about almost 2 weeks away. It's a week from this upcoming Friday. And so we decided, just to keep things as normal as possible for our students, we decided to go ahead and offer the Integration B this year. It'll be done virtually, but you can click on the links there and you can see all the information about the Integration B this year. The main thing to note, one of the main things, obviously, is that the B itself occurs on Friday, April 30th at 2:30 p.m. on Zoom. The Zoom link to the Integration B is provided right there. And then registration for the B, which is it's free registration, you just sign up for the B, is due by this upcoming Sunday. So a week basically from today. It's going to be due. The registration's due. And the official rules for the Integration B, these are only slightly changed from the official rules from the past. So contestants you guys meet all these conditions right here, so I don't really need to read the eligibility requirements. You cannot be a two-time champion and still participate because it makes it no fun for everybody else. We've had that situation in the past. So, and let's see, then you must submit your entry form online by this upcoming Sunday at midnight. Technology requirements, the same requirements we've been using this entire time. You have to have internet access, a webcam, a scanning tool. That just means a phone. Your hands and paper must be visible on camera at all times, including while scanning and uploading. Scanning apps I'll have to let her know that that's misspelled, such as Adobe and Notes on mobile phones are free options. Finalists must use Sharpie, fine point pens, or similar markers in round 2 to ensure their solutions are visible. So what's going to happen for those who make it to the second round is that you'll do your integrals, you work on your integrals, it'll be visible while you work on them. And then when you are done, you will hold up. And so you can see, because I do not write in very dark ink, you can't see very much. So that's why we're saying we'd like you to write in Sharpie so that we'd be able to see your work. And then just hold it up to your camera and the judges will be able to judge. Competition rules, you must correctly evaluate indefinite single variable integrals in the time allotted. Generally, the way it works is I'll put up an integral and we'll say you have 2 minutes. And then you sit there and madly try to do it in 2 minutes or something like that, or maybe 3 or whatever it is, depends on the integral. And and then we'll say pens down, and you either scan if you're in first round. So the first round, you would then scan your work and send it in, and you get like a very short period of time to do that. So you want to make sure that you know how to upload that stuff. You don't have like 10 minutes to upload it. It'll be like 30 seconds. All participants will be given the same integral. And basically what happens is we do this over and over again. So integral 1, you have a minute. Integral 2, you have a minute. Integral 3, you have a minute or two, something like that. Once we get down to maybe 5, 6, 7, or 8 integrals in, we then say, okay, let's take a break. We're going to grade all these very quickly, just right or wrong. Okay. And the constants of integration are not necessary, so the plus C doesn't matter. But we go through and grade for correctness, and we basically find a good cutoff. So it's not necessarily that if you got one wrong that you're out. It just we start kind of going through it, and we start with the idea of a double elimination. But if it ends up that it's just getting way too long, we basically take those who have the most right after the certain amount of integrals, and they form the contestants for round two. Now, the round two contestants are again visible to everybody, and we show the integral, but these integrals are a little bit more challenging. We'll say you have 5 minutes, whatever it is, and then when the time's up, everybody holds up their integrals, and so on and so forth. It kind of repeats the same process. The methodologies that will be employed to evaluate a given integral are, I dislike that they wrote all these in. It's the standard ones you've learned: substitution, integration by parts, trig subs, integrals involving trig functions, partial fractions, rationalizing substitution, which just means radical subs, and yeah. So no electronic devices. And for round one, once the integral is evaluated, contestants will turn their final responses face down and wait until further instructions. Anyway, you can read all this. It sounds like a lot, but it's actually not. It goes pretty quickly. Because we're virtual this year, you get bragging rights, but we don't have a prize list right now. But still, it's a fun time. So, and it's a short period of a Friday, so I highly recommend signing up for it if you want to. And I create a little study guide over the weekend, because if you take a look at our older assignments in chapter 7, a lot of the instructions said like, oh, integrate this by parts or something like that. I really dislike that, because during the integration piece, it's just going to be evaluate. That's all you're going to see over and over again. So I put together, I think, 113 problems. You don't have to do these, totally optional. But it's a good kind of test, right, to see if you can power through some of these. Some of these are going to be harder than others. I just grabbed a bunch of problems, so some of them will take longer than 3 minutes or max 4 minutes. Partial fraction decomposition problems are notoriously a lot longer. Oh, look at that, partial fraction decomposition. So you want to try to kind of power through. I tried not to grab like beastly problems, but there are a couple in here by accident, I'm sure. But there's stuff like this that should be super fast for you. And notice the instructions: just compute, right? Evaluate. There's no instruction like, you know, uh, compute using partial fraction decomposition or something like that. So anyhow, I highly recommend that you just go through and try a bunch of these. It's kind of fun. It's a great challenge. These are all completely randomized in the background, so you don't have to go through all of them or even one of them if you don't want to. But I'm just throwing it out there that we have the option. All right. So I hope your weekend went swimmingly. Anything else I need to say while I'm on the My Open Math website? Not really. Oh, I didn't sort of. I moved the date of our upcoming exam because I wanted to make sure that you had time to turn in the assignment for 11, 10, 11. So I moved the exam 3 date to actually be the same day as the integration B. Sorry about that. But I just thought that it would fit a little bit better so we're not so rushed. We're coming into the home plate here, and so I want to make sure that you have the time to kind of digest information, especially at the end of chapter 11. It tends to be a lot. It feels like a lot. Chapter 11 does. And we have a quiz today on 11.6. Wait, no, 11.5. Sorry about that. So just a heads up on all of that. Now I'm going to go ahead and go to my laptop and see where we were. right? I just uploaded a bunch of stuff into my laptop as far as for this upcoming lecture. So I want to make sure that I have everything done. So last time we were doing representations of functions of power series, one power series to rule them all. And everything was based upon the summation n equals 0 to infinity of x to the n. And this power series is the geometric series, right? It's something, a common ratio to the nth power. So we know that if it converges to 1 over 1 minus x, as long as that variable x is less than 1 in magnitude. So that is kind of entertaining. And so that gives us our first full-fledged power series that we can actually find a function for. However, as I mentioned during class, it's not like you're always just going to be handed a function 1 over 1 minus x. You'll be handed modifications of that. And so that's what we did last time. We dealt with the function 2 over 9 plus x. And we modified that to be more like 1 over 1 minus something. And by the way, I uploaded these videos as well from last class. I finally got around to that. And we visualized those as we move forward. Now, just to give you a heads up, my lecture notes are going to have a little hiccup in them in a moment here, but we did this guy right here, and we rewrote that as 2x squared times 1 over 1 minus something. You can see it over here. So that's the goal. You can see that I'm constantly just saying, get it to be something like 1 over 1 minus something else. Now, let me go ahead. This is online content I was recording. So there are two examples in this lecture, this section, where I put online, where I recorded online video lectures for that one and that one. So I just want to give you a heads up that that those will be online. All right. So we're going to pick up today with this guy. Find a power series representation and determine the interval of convergence. And this is just to reinforce basically what we've been going through. What you want to do is somebody hands you a function, you're really hoping that you can somehow write this as something like a number over 1 minus something. I mean, that's the general idea. However, if you take a look at this function, it's actually got a function in its numerator, and there are two ways you can go about doing this. You can either split it into two separate functions, or you're more than welcome to do this. You could say, well, you know what that is? That's like 1 plus x times 1 over 1 minus x. You're totally welcome to do that. That is a legitimate move. And so we happen to know that 1 over 1 minus x is the functional representation of the power series. Let me go ahead and zoom out because my ink is going to be ridiculously large here. The power series n equals 0 to infinity of x to the nth. And we do have to make mention where the absolute value of x must be less than 1, because the reality is otherwise that power series would not converge. It's a geometric series, and it only converges if its common ratio is less than 1 in magnitude. So that is the beginning of how you would find the power series representation for this function. Right at this beginning, though, I can easily tell you, since the since we have the restriction that the absolute value of x is less than 1, that would imply that x is between -1 and 1. And what we were doing in the previous sections, 11.8, which was power series, is we were checking those edge points. Like, oh, does it converge at 1? And does it converge at -1? Or does it converge or diverge at 1 or -1? However, when you're dealing with power series based upon the geometric series, I'll go ahead and make a green little note here. Since that power series is based upon the geometric series, since this is based on the geometric series, we cannot include endpoints. Oops, plural. You cannot include endpoints in its interval of convergence because, again, the geometric series is never going to converge when its common ratio is a 1 or a -1. So you don't have to worry about checking the endpoints when your initial power series is based on the geometric series, which is basically means that you have x to the n, or maybe x minus 2 to the n or something like that. But basically it's something to the n. That is a rarity, but if you can get it, take advantage of it, because then you don't have to check the endpoints for convergence. And so now we know the interval of convergence for this power series, once we clean it up, is going to be a -1 to 1, not including the endpoints. Again, because it's based upon a geometric series. So geometric series, you don't include the endpoints in the convergence. Now, I said that we're almost done. It's because technically you would probably not leave this power series written this way. You would actually distribute this series to each of these two terms. It's kind of a half. It's 6 in one hand, a half a dozen in the other. That's not what I mean to say, which is basically that there are some instructors that will force you to do this and some that won't. And because I don't know who your future instructors are going to be, I'm going to force you to do it so that it covers both cases. Okay. So let's go ahead and distribute that power series through. Not that you had to, but obviously that power series times 1 is just the power series itself. Plus the power series times x is x times the power series. And you would think, okay, so I'm done, right? Nope, you're not done, because you can take this x, let me go ahead and find it. There we are, this x right here, and you can pull it into the power series to increase the power of that x to the n by 1. And so that's what I'm going to do here. This is, generally speaking, not everybody's favorite thing because it's just a lot of little bitty steps here, but it's good to kind of see them. So we have the sum of these two power series, which are both, by the way, convergent. We are forcing them to be convergent by saying that x is between -1 and 1. So these are just some finite functions here. They're actually convergent to some type of function. And now the very last thing that you technically could do here is you could glue these together as a single series. I don't know of very many instructors who would force you to do all this work. So I can't say that I would want you to do this. It's just that I need to showcase this so you know that this is what some instructors might force. I think it's kind of silly to force it in this case, actually. This is a very unique case where it's not that big of a deal to go from here all the way down to here. These are all equivalent statements, in my opinion. So, and I would accept any one of these. All right. So that is actually the power series representation of f of x equals 1 plus x over 1 minus x. Very fast, kind of nice power series to deal with. But let me ask you if you have any questions on that, if there's anything that you're, maybe a little bit confused about there. Remember, these power series, you can visualize them in Desmos by using the sum formula in Desmos. That's such a good way to visualize what power series are and what you're doing this entire time. So let's go ahead then and hop forward. We're gonna skip a page here in a moment. Come on, hop. That's the online one that for some reason I have 2 pages of. Now we're going to switch into, we're still in section 11.9, but we're going to start talking about the calculus of power series. Now, calculus power series is actually why you learn power series. So it is important that we spend a little bit of time on this. So let's start with the statement. If we have a power series, n goes from 0 to infinity, it's a summation, and we have some constants here, c sub n, and we have it centered at a. Remember, that's what that a is. It's the center. And we raise that x minus a to the nth power. That's the power series. If you were to, again, expand that out as an infinitely long polynomial, it would look like the following: c naught plus c1 x minus a to the first plus c2 times x minus a squared, and so on and so forth down the line. Just an infinitely long polynomial. So if that infinitely long polynomial, which is that power series, has a radius of convergence greater than 0, and we've actually seen an example of a power series with a radius of convergence equaling 0. So let's pretend as though we have a power series that has a non-zero radius of convergence. So there is some interval over which it converges. Then we can define the following. The derivative of the power series is going to be this. Now, I don't want you to think you have to memorize this, because you should just know this. I'm going to prove it right now. Suppose that f of x was equal to that summation n equals 0 to infinity of c sub n x minus a to the nth. And suppose you just go ahead and you say, I'm just going to expand that out a little bit. So I have c naught, we did this just a moment ago, c1 x minus a to the first plus c2 x minus a squared, and so on and so forth. And you want to find out what the derivative of this function is. Well, I'm going to skip over the center for now, and I'm just going to take a look at what we're used to, the derivative of a polynomial. Well, the derivative of c1, a constant, times x minus a, so that derivative right there, well, the derivative of x minus a is 1. So it's 1 times c1 plus the derivative of this piece right here is going to be 2c2 x minus a to the first times the derivative of x minus a, which is just 1. Let me go ahead and throw one more in there. That's supposed to be a cubed, but got kind of wacky. Okay. The derivative of that next term is going to be 3c sub 3 x minus a squared, and so on and so forth down the line. Notice that we're missing a term. So when we took the derivative of this power series, the constant disappears. So I'm going to write a little note here. That's actually a 0. This disappears because, well, you took its derivative, and derivative of constant is 0. So you lose a term in your power series expansion if, and by the way, this is a big if, because if you look at the text, it's somewhere in the text. The author does not make a big deal about this, but this is actually a huge deal. You will lose a term if your original function had a constant term in it. So the point here, I will just write this as a punchline. Oops, punch. If the power series had a constant term, the derivative will have one fewer term. Well, one less term. than the original power series. So our original power series started at n equals 0 and went to infinity. However, note when I take its derivative, we don't start at n equals 0 anymore. We're starting at n equals 1. So turns out our summation for the derivative is from n equals 1 to infinity. Now, just pretend as though you're taking a derivative of this. It's n times cn x minus a to the n minus 1. I'll write that down. It's n times cn times x minus a to the n minus first power. It's just basically like taking a derivative, except that you have to make sure if your original function, your original power series expansion, had a constant, you're going to have to re-index. Basically, it'll start one higher. So that's just a heads up. And actually, it's not necessarily true that it'll start one higher all the time, but at least for Calc 2, it is. Okay. Or I should rephrase that. It's not that it will that when you take a derivative, it will always re-index. That is not actually true, because sometimes you're handed a power series that doesn't start at 0. You might have been handed a power series that started at 27. Well, if that's the case, you're starting at the 27th power for your function, and nothing disappears when you take its derivative. You can take the derivative of each one of the terms if it starts at the 27th power, and nothing will disappear. So your derivative will not re-index at all. Just be highly aware of that. So each time that you take a derivative of a power series, you just want to ask yourself, is there a term in that that's a constant? Because if there is a term that's a constant, I'm going to have to erase that term from my summation, essentially. And that's what we did there. Okay. So you don't have to memorize this formula. This formula right here is honestly just the derivative of that guy right there. And because the first term of the expansion was a constant, we start at 1 with the derivative rather than 0. And again, just watch out. Sometimes in differential equations, you don't have a constant term in your expansion, and so there's no need to re-index. All right. So that's the first part of the calculus of power series. The second part is integration. So again, remember, we just have an infinitely long polynomial. So if our polynomial is this guy right here, when you integrate that, you're going to add 1 to the exponent and divide by the new exponent. Well, that's literally what I just did right here. But notice I have a plus c out front. That's because when you do an integral, you get an extra constant. Just like when you take a derivative, you remove any constants. When you integrate, you add constants. So you're going to gain terms when you integrate, and you'll possibly lose terms when you differentiate. I've always thought about this as climbing a ladder, if you will. So if you think about a ladder, I don't know why this makes sense to me, but let's just say that you're in this ladder right here, the ladder of calculus, I'll call it. So you have some function, and then you have its child function right here. The child function is called f prime, and you have its parent function above. The parent function we'll call capital F for the antiderivative. Okay. So the child function, it loses information. So when you go from the parent to the child function, information gets lost. You lose constants, for example. When you take derivative of a constant, so if your function f had a constant, when you take its derivative, that constant will disappear. On the other hand, when you integrate a function, so you go to from the child to the parent, you gain information. Specifically, in this case, a plus c. And that's the idea I've always kind of thought of when it comes to the ladder of calculus, right? You have your function, which is the rung that you're currently standing on. If you go to the parent function, the one above that, the antiderivative, you gain something. So it should make sense. The power series, when I integrate my power series, I will not only integrate just the pieces of the power series, add 1 to the power, divide by the new power, but I'll gain a constant of integration. Okay. And then with differentiation, you lose, right? And then let's see. Both of these functions, both the antiderivative and the derivative of your original power series, will have the same radius of convergence. However, the interval of convergence might change. So clarification, I'm not going to read that clarification. I'm going to actually write that little note here. I'm going to say, however, the interval of convergence might change. So the radius of convergence, remember, that's just from the center to the edges. How far is that distance, right? But the interval of convergence is the actual interval you're talking about, and it could include or not include those endpoints. Well, let's think about this in terms of the ladder of calculus. Let's suppose that F had an interval of convergence, let's just pretend, from 1 to 3, including 1, but not including 3. When you take its derivative, you lose, possibly, I should say, info gets lost, and I'll put in here possibly, right? Because there are times when you don't lose information. For example, if F didn't have a constant, when you take its derivative, you still have the same number of terms. So you don't actually lose anything. However, if F did have a constant, you lose that constant when you take its derivative. Well, the same idea goes for intervals of convergence. Let's pretend, my interval of convergence for my original function F. When I take the derivative of my original function F, the interval of convergence for its power series might be the same. Whoops. Yeah, that's good. Might be the same as the original, or you could have lost an edge. You'll never gain an edge when you take derivatives. You might keep the edges or you might lose an edge, but you'll never gain anything. Gaining is for anti-differentiation. Losing is for differentiation. Let me write that in black so my color scheme actually is matching. And let's go to the antiderivative. Now, when you go to the antiderivative, you could possibly gain information. Specifically, when you take the antiderivative, your interval of convergence, which was a closed half open interval from 1 to 3, closed at 1, open at 3, it could be the case that it's still the same interval of convergence. Or you could actually gain that right edge point. You won't lose anything, I promise you, but you'll gain possibly by taking the antiderivative. It's a pretty decent, solid example of how you might gain or lose information when you take antiderivatives or derivatives of power series. I'm going to take a drink real quickly here. All right. So let's go ahead and hop forward one and find a series expansion for this bad boy right here. For the derivative of this bad boy right here. Sorry, not for this guy, but for F prime. Well, here's F. If you were to take F prime first, that would be very, very challenging. Not because it's hard to take the derivative. It's not hard to take the derivative. But if you were to take the derivative, I'm just going to go ahead and write that off to the side. F prime of X is equal to quotient rule 6x to the 5th times 1 minus X minus x to the 6 times the derivative of 1 minus x, which is a negative 1, all over 1 minus x quantity squared. If you take a look at that, that will clean up very slightly. Let's see, we have x to the 6th minus 6x to the 6th, so that's a negative 5x to the 6th, plus 6x to the fifth all over 1 minus x squared. And that's pretty much as good as it gets. I mean, you can factor out the x to the fifth, but nothing else is going to help out. Let me make sure I did my mathematics right. 1, -5. Yep. So that would be the derivative of our original function if we were dealing with Calc 1. We're in Calc 2, though. And they're asking for a power series representation of this. It's a really good example because if I just started you with this and said, hey, find the power series representation for this, we would all, myself included, just stare at this. I don't know, right? That's exactly how we would all look at this. It's very, very difficult given a function. It's very, very often very challenging to derive its power series, at least at this point in the game. But they were kind enough to start us with the original function. And so if instead I come into the room and I just say, hey, here's a function, could you find this function's power series and then take the derivative of that? That answer should be, oh yeah, totally, I could do that. The power series of this function, well, that's x to the sixth times 1 over 1 minus x. There's my 1 minus something in the denominator. Perfect. I know the power series representation for that 1 over 1 minus x is going to be a summation n equals 0 to infinity of x to the nth. Great. And I might as well bring that x to the sixth inside. When I say I might as well, I mean you're going to have to, right? So I'm going to take that x to the sixth, I'm going to bring it inside here, which means I'm adding 6 powers to that x inside. So I'll go ahead and say this is equal to the summation n equals 0 to infinity of x to the n plus 6. I feel pretty good about that. That's the power series representation of f, not f prime, but of f. I should also note here that the interval of convergence is -1 to 1, because if you take a look at that right there, that is the common ratio for our geometric, in quotes here, geometric series. And we know that only converges if the common ratio is less than 1 in magnitude. So it's centered at 0, and the interval of convergence is -1 to 1. All right. So let's go ahead and now take the derivative of this power series. And after my conversation with you just a moment ago on all this stuff right here, you would think that when you take the derivative, we're just going to basically take the derivative of the argument of that series and increase the n to go from 0 to start at 1. But that's actually not the case. It's a really good example. Let's see, taking the derivative, f prime of x is equal to, I'm going to write it this way. It's equal to a sum. I'm not going to tell you the index of the sum. I'll just say it starts at n equals something, ends at infinity. And I'll take the derivative of x to the n plus 6. You bring down the power, and you reduce 1 from the power. That would be the derivative, but we still have to figure out the index. Does the index change or does it stay the same? That's a critical question. So let me go ahead and link these up and say, do we change index or not? And the way you can easily find out very quickly is write out a few terms of this series, this power series, the original one we're about to take a derivative of, and see if any of them are constants. Well, when n is 0, you start at x to the 6th. When n is 1, it's x to the 7th, ... And none of those are going to be constants. Punchline here is you are not, when you take the derivative, you're not going to lose a single term. So this is a case where when you take the derivative, you don't increase the index because you're not losing anything. And that is something that the author of our text doesn't really give a big stink about, but it's true. You do always given, Avi, I'll say it right this way. When you're given a power series or a function and you write the power series for that function and you're asked, hey, I need to take the derivative of that. It's one single question really that you need to ask yourself as you're taking the derivative. You just need to ask yourself, do I need to change the index or not? And the way you can determine that is look at the original power series you're about to take the derivative of, this guy right here, expand it out a little bit and see, are there any terms that will turn off when you take their derivative? And the answer here is no. You have x to the sixth plus x to the seventh plus x to the eighth plus x to the ninth and so on and so forth. All of the derivatives of those are still going to be there. There's no constants. No constants. And so because there's no constants in this expansion, don't add 1 to index. The only time you're going to add 1 to the index or modify the index, I should really say, is if you have a constant in your original power series, because that disappears. And so you need to basically start, you don't have the same number of terms in your derivative. So you're erasing one term. So you erase the 0th term, and now you're going to start the first. But that's not the case here because our original function just didn't have a constant in its power series. And by the way, little end note here, that is the series expansion for f prime, and we know what f is as a function, so we know that this is the power series expansion for negative 5x to the 6th plus 6x to the 5th over 1 minus x being squared. It's a bit of a mess. That's why I said if I had started you off with this function and said, hey, find a power series, it would be nearly impossible. It would be very, very challenging given this to just say, find the power series for that. That would be terrible. But if somebody said, oh, guess what that is? That's the derivative of this guy. Then I'd say, great, I'm going to find the power series for this guy and take its derivative. That's just much easier to do. So we have to start thinking in two different worlds right now. You have the world of functions that you're dealing with, and you have the world of power series that you're dealing with. And when you step into which world just depends on how easy it is. So let me give a visual for that because I've never really said that in any class, but I think that that's a good way to think about it. With the world of functions, that's what we're used to. And we have now a brand new world called the world of power series. That's something we're not used to, right? And for most functions, they do have a related power series. So we have f, and then we have some power series of f. Power, I'll just say ps of f, if you don't mind. Power series of f. We have f prime, for example. So we have a power series of f prime. We have f double prime, right? So we should be able to find a power series of f double prime, and so on and so forth. Also, we have the integral of f. So we should be able to find the power series of the integral of f. But here's the deal. Where you start is going to be an art form here. So in this case, they said find a power series for f prime. Okay, great. So here was our goal. Let me highlight it. I'll point and arrow at it, and I'll say goal. That was our goal. Find a power series of f prime. However, what were we given? We were given the function of f. I just got email. Okay. We're given the function of f. I have to map a road to get over to this point. And there are two directions I could go. There's actually several directions I could go, honestly. So let me showcase all the directions. You can't do a diagonal. You can't go this way, but you could transform f to its power series and then go from the power series of f to the power series of f prime. Or you can go from f to f prime and then magically somehow say, oh, and I know the power series for f prime. Those are the two ways actually you can get from our given information to our goal. That's the only two directions you can go, right? I actually kind of like this mapping. This kind of works nicely. And if you think about both those directions, taking f and transforming f into a power series, easy. Taking the derivative of power series is always super easy. You're taking a derivative of a polynomial. So that is the easy route. Easy. Technically, if we had done the other route, they gave us the function f. Well, it is somewhat easy to take its derivative of the function. But then going from the derivative, here we are at the derivative, and somehow magically saying what the power series is for that is hard. So of those two directions I could have gone, you better believe I'm going to go this direction right here. I'm going to go this easy route and then this easy route. Man, I like this visual. I'm going to use it. I've never done that before, but that seems to me to be a nice way of viewing this stuff. And I'm probably saying that because I know what's coming up. So, all right, let's go ahead and see how convoluted this can get. We were very lucky in this case that somebody handed us the function and said, hey, just find f prime, the series expansion for f prime. But what if they don't do that? What if instead they give us a function and say, find the power series for this function, but they don't say find f prime or the integral or anything like that. So let me give you an example of what I'm talking about. And there's a little advice at the beginning. When trying to find a power series representation for a function that is not a rational function of the form something over a plus or minus bx, in other words, it can't be written easily as 1 over 1 minus happy face. Right? If you can't write it like that, it's better to ask yourself, what would I integrate or differentiate to get to the form they've handed me? Okay. That's probably a good way to do this. So somebody hands you this function. F is negative 8x to the 7th divided by 1 plus x to the 8th squared. And they say, find the power series. I'm going to go ahead and build that table. I just think that table is going to be kind of nice. So function world. And power series world. All right, let's write down what we're given. And I'm really digging this. We're given a function which is equal to a negative 8x to the 7th over the quantity 1 plus x to the 8th squared. We want its related power series. We want power series of f. Now, I don't know about you, but looking at that function and just immediately transforming it to the power series does not look like a good idea. I think that directly going there looks to me to be hard. So that is not going to be likely the best direction to go. However, let's work in our function world for right now. Since I can't seem to get a power series out of this, I'm just going to go ahead and play with my function a little bit. And the only thing you can really do with a function is either integrate or differentiate. Do you see what the integral of this is going to be? Maybe I should say it this way. If you differentiate this, I'll leave a little bit of a placeholder in between. I'll say f prime of x is equal to, if you were to take the derivative of that given function, you would have a quotient rule. And the quotient rule would be just nasty. Negative 56x to the 6th times 1 plus x to the 8th squared minus a negative 8x to the 7th, so plus 8x to the 7th, times the derivative times 2, 1 plus, it's just a mess. Dot, 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 dot. It's a mess. And again, that becomes an absolute mess. There's just no way that I'm going to write that as a power series. So maybe if I integrate f, it would be cleaner. So let's think about the antiderivative of f here. Like, what is it that you would take the derivative of to arrive at this f? Well, if I take a look at that right there, and let me just off to the side do this computation. Let's see. I'm going to let u equal a 1 plus x to the 8th so that du will steal. Ugh, my handwriting is just terrible. Du will steal an 8x to the 7th dx. Okay. So notice that I have an 8x to the 7th dx to steal away. Great. So this is going to be a negative 1 over u squared du. And that's going to be a negative u to the negative 2 du. You would add 1 to the exponent, divide by the new exponent. So there'll be a positive 1 over u plus c. Or in other words, 1 over 1 plus x to the 8th plus c. Now, let me ask you. So all we did when we went from f to this was an easy integral. It wasn't too terrible. I'm not going to say it's super easy, but it wasn't too terrible. We did an easy integration. Now, could we find the power series for that easy function? And the answer to that is sure. I could possibly find the power series for that easy function. So let's go ahead and do that. Let's find power series for 1 over 1 plus x to the 8th. Notice I don't include the plus c because the plus c is just a constant of integration. You'll see what happens that in a moment. Well, 1 over 1 plus x to the 8th is the same thing as 1 over 1 minus a negative x to the 8th. Remember, our goal with these power series right now is to get them in the form of 1 over 1 minus. And that is exactly what this is. So the power series for this is going to be the summation n equals 0 to infinity of a negative x to the 8th to the nth power. And this can be written as the summation n equals 0 to infinity of a negative 1 to the nth. That's supposed to be an nth, but there we go. Times x to the 8n. All right. That wasn't too terrible. So I happen to know the power series. Let me write this over here in black ink. Power series of the integral of f is equal to the summation n equals 0 to infinity of negative 1 to the nth power, x to the 8n. And remember, actually, that integral of f has a plus c. So I'm going to write a plus c as well. Plus c. It's not within the summation. It's just an extra constant. So let's see. We're given, that's our starting point right there. And we have an ending point or a goal. Our goal is to arrive right here. We want a power series for f. Well, I have a power series for its integral. How am I going to get from this power series? So it's just a like a map, a road map. How am I going to get from this power series right here? Sorry. How am I going to get from this power series right here, the power series of the integral of f, to the power series of f? How am I going to get there? Differentiate. Yeah, you better believe it. Differentiate it. Yeah, if you differentiate this power series we just found, because this power series is the integral of f, differentiating will give us the power series for f. Boom. Kind of nice. And had I done this ever before, as far as writing it this way, I would have probably ordered the integral stuff to be above my function. And if I needed to take derivatives, I would have put it below, just because I like that visual of the ladder of calculus. But for right now, this works. So if I want to differentiate this power series, that'll be an easy move. Let's go ahead and now differentiate the power series of the integral of f. Let's go ahead and take that derivative with respect to x of the summation n equals 0 to infinity of -1 to the nth x to the 8th n. And remember, you have that plus c, but as I mentioned a moment ago, that plus c actually will not play a role, because the derivative of that constant disappears. And Veronica, you're saying the right thing. Do we have to worry about reindexing when we take the derivative of a do we only have to worry about reindexing when we take the derivative of a power series? Yeah, you only have to worry about reindexing when you take the derivative. And in this case, we're going to worry about it because if you write out the first few terms of this power series, when n is 0, you get x to the 0th, which is 1. When n is equal to 1, you get a negative x to the 8th. When x is 2, you get a positive x to the 16th, and a negative x to the 24th, and positive . So we will worry about reindexing here, because when you take the derivative, this disappears. And so we are going to have to reindex this one. So this will be the summation n equals 1, because the very 0th term disappears to infinity. Remember, -1 to the nth is a constant. A lot of people get thrown off by this, and they think they have to move that n out front. No, bad us. Don't do that. All right. It is not, you do not have to take that n and pull it out front. That's a constant. So it's just still a -1 to the nth. The piece that we're actually differentiating is the x. I have x to some power. When I take the derivative of x to some power, you drop the power down and you reduce 1 from that old power. And there you have it. That is actually the power series for f, because that's the derivative of the power series for the integral of f. So let's go ahead and write that up above. That was our goal. I just want to put it here. This is equal to the summation n equals 1 to infinity of a, you could probably move the 8 out front if you want to, -1 to the nth n, oops, that was supposed to be an n, x to the 8 n minus 1. Not so obvious, right? It's not obvious that that was what this would turn into at all. Just writing it here as well, so it's complete. There we go. So a lot of beefiness to these problems, but I actually love that function world versus power series world. Where are you starting? Where do you want to end? And you have to find a road there. You can't do diagonals. So you can't, it's illegal, maybe I should say, to go diagonally across because you're skipping steps when you do that. So you want to only do vertical or horizontal movements on this map. And you want to take the path of least resistance. You want to do easy road trips all the way. If you just try to go directly from the given function to its power series, good luck. That's going to be incredibly difficult. Okay. Really like that. I'll try to clean it up as we move forward. I think that's a great one. Maybe I'll redo one of the videos I recorded to do this because I think it's so neat. All right. Other questions about that? I'm going to mute myself and take a drink here. All right. So let me hop forward. Now, this one is when they explicitly say, hey, I want you to integrate this. That's actually a lot easier, to be very honest with you. But let me just do all of the work that we had done previously, just to showcase how this is set up. So I'll start with my little table that I've been creating now. So I think that's kind of neat. So here's our function world in our power series world. Okay. And I'm going to this time do this. I'll just have 3 rows here. One row I'll dedicate to f. One row will be dedicated to its parent, which is the integral of f. And one row will be dedicated to its child, which is a derivative of f. Now, just letting you know, you will probably not use all 3 rows. In fact, you won't. But let's go ahead and start with this. Our function, don't worry about the integral. Our function is x squared over 1 plus x to the 4th. That's what our function is. X squared over 1 plus x to the 4th. That is where we're going to start. That's what we were given. All right. And we want a power series to approximate the integral. So in other words, I want the power series of the integral of f. So I want to end in this top quadrant, top right quadrant. I'm going to end right there with the integral of the power series of the integral of f. So let me write that in. Power series of the integral of f. That's where I want to end. Now you can see the roadmap. The roadmap, you're either going to go up and over, or you're going to go over and up. Well, let's see. We'll at least start with this function here. You have your choice. You could try to integrate this function. I'm going to let you know right now, integrating this function is not a joy. Integrating this function by hand is going to be a bit of a mess. And in the end, if you get to a bit of a mess, let's just pretend, because we now know how to integrate things. If we integrate that function, so let me just write integral of x squared over 1 plus x to the 4th dx. It's supposed to be a 1. If you try to integrate that, you have some substitution techniques. Avi just sent me a message. Wouldn't it be much easier just to find the power series of f? You better believe it. Yeah. So this looks hard. Hard. But just kind of drawing your attention to this, even if you got the power, the function form of this integral, let's say you integrated this, you found out what that is, then turning that into a power series, Impossible, maybe? I'm not sure. It'll be near to it. How's that? It's very, very challenging. However, just what Avi had sent me a message about, I think it'd be much easier just to write the power series of this function. Path of least resistance, right? So let's go ahead and just find the power series of f. So here's f, x squared over 1 plus x to the fourth, which is the same thing as x squared times 1 over 1 minus a negative x to the fourth, right? So that is x squared times 1 over 1 minus something. And that's exactly how you want everything to be, is 1 over 1 minus something. And so this will turn into x squared times the power series, starting at 0 and going to infinity, of a negative x to the fourth to the nth power. Now that should be cleaned up. So let's go ahead and clean that up. That's going to be the power series of n equals 0 to infinity. We'll have a negative 1 to the nth. We have x to the 4n, and we're adding 2 more powers. So it's going to be x to the 4n plus 2. Great. That was pretty easy, actually. So series n equals 0 to infinity of a negative 1 to the nth, x to the 4n plus 2. Yay. Now, integrating that to get to the parent function, super duper simple, because you're just integrating a polynomial. That is going to be very, very easy. So let me go ahead and erase all my ink here, and I will just point an arrow up. This is going to be really, really easy, and we'll showcase that right now. Easy is a dangerous word in mathematics because people who don't see it are going to get frustrated. So I shouldn't say easy a lot. I'm just going to say it's not as challenging as the red ink path. Okay. So let's go ahead and integrate our power series. And remember, when you integrate, you're not going to reindex. That was something that Veronica had asked. Are we only worried about reindexing if we differentiate? Yep. When you integrate, you're not going to have to reindex. So it was a really good question. Negative 1 to the nth, x to the 4n plus 2 dx. Great. Wonderful. Now, when I integrate this, it's going to be... let's see, the summation. I'm going to put C out here, C plus, because when you integrate, you get a constant of integration. Summation n equals 0. Notice I didn't reindex because you don't when you integrate. You get just an extra constant that pops out. That's all. Let's see. The negative 1 to the nth is considered to be a constant in terms of the integral. We're going to add 1 to the power of our exponent and divide by that new power. Now I got to tell you, that's pretty rad. That is not bad. So our integral, this is by the way, the indefinite integral. Our indefinite integral is C plus the summation n equals 0 to infinity of negative 1 to the nth, x to the 4n plus 3 over 4n plus 3. Yay. We started, we got to the end. However, the question never asked us to do all that. It says use a power series to approximate the definite integral. But it's a definite integral. So we need to evaluate our power series from 0 to 0.3. So we need to do that here. One thing I do want to mention is that, let's see. I think that C, because of definite integral, that C is not going to come into play, right? Definite integrals, do not have a plus C. And sorry, I have a sticker in my sock that has been bothering me this entire time. Sorry. It's random. All right. Okay. So anyway, that plus C, when we evaluate a definite integral, you never have a plus c. So this definite integral, this is going to be, don't worry about the plus c, it's going to be the summation from n equals 0 to infinity of -1 to the nth x to the 4n plus 3 over 4n plus 3. That was the antiderivative, and we're evaluating this from 0 to 0.3. All right. So plugging in the top. So far, I hope this all makes sense. Where we started with the original function. We needed to arrive at the power series for the integral. So we had two paths to go: integrate the original function and find the power series for that. Impossible. Or start with the original function, find its power series, pretty easy, and integrate that. Great. And now we're going to evaluate that from 0 to 3.3. Sorry. If you plug in a 0.3 and you plug in a 0, you will get the following. This is going to be the summation n equals 0 to infinity of a -1 to the nth 0.3 to the 4n plus 3 over 4n plus 3 minus, if you plug 0 in, it's just going to be 0. Right? If you plug 0 into this power series right there, you'll just add up a bunch of zeros. So that's okay. Well, great. We found what this definite integral will turn into. But who's got all of infinity to add that up? Not I. I don't have all the time in the world to do that. And I'm supposing that you don't either, right? So how are we going to find or estimate the value of this? Well, you could just add up the first few terms and cross your fingers that you've done enough, right? Let me clean this up and just say this is the summation n equals 0 to infinity of -1 to the nth. There's really not much I could do here. 0.3 to the 4n plus 3 over 4n plus 3. Not much. It wasn't much of a change. I just didn't like the -0 hanging out there. So we could add up, let's say, the first 2, 3, 4, 5, 1,000 terms or something like that, and hope that we are approximating the actual value of that definite integral to 6 decimal places. Or we could do something very intelligent. Note, and this is going to be the trick to a lot of problems. Note, this is an alternating series. Right? It goes, it's positive, then negative, then positive, then negative, then positive, then negative, then positive, then negative, and so on and so forth. We know that this series will converge because it's built off of this guy right here. And that is that's a geometric series. So we know this series will converge from -1 to 1. What we plugged into it was between -1 and 1. Believe it or not, we plugged in a number between -1 and 1. The number we plugged in was a 0.3. This problem is designed so that you can actually evaluate it. So the value we plugged in for x right there was between -1 and 1. So we're guaranteed that this will converge to a value. To find that value exactly might be impossible, but to estimate that value, we can use the error estimate for the alternating series test. The error estimate from the alternating series test is, it shouldn't be the absolute value. The error for the nth term, if you add up the first 10 terms, the error for that summation from the true value of the summation will be always less than or equal to the next term in line from the alternating series. It's the easiest of all of the error estimate tests. That's why I like it. So how are you going to find out how many terms to add up? Well, you want the n plus first term to be less than 0.0000005. Let me say that again. We want the error, which I'll point at this right here. The error is bounded by b sub n plus 1. Okay. We want the error to be less than. And now here's the deal. You want 6 decimal places of accuracy. The way you can guarantee 6 decimal places, this is the first time we're having this conversation in this course. Normally they say, hey, I want your error to be less than 0.01. That's easy. If they say we want the error to be less than 0.01, then I just say, well, great. I want r sub n to be less than 0.01. That is, I want this number to be less than 0.01. Okay. However, when they say I want 6 digits of accuracy, that means I need to lock in the first digit. I can't have error at the second digit. I can't have error at the third digit or the fourth or the fifth. And technically, I don't want error at the 6th digit either. First through 6th digits. But I'm allowing for a rounding digit at the 7th place. And that will guarantee me precision up to 6 decimal places, is that I lock in the 6 decimal places and I allow for the rounding at the end, the 7th decimal place, to round to the appropriate value at the 6th. That's what that 5 at the end does. So this is why I said we want it to be less than 0.0000005. So we want b sub n plus 1 to be less than 0.000000 and then a 5. Because remember, our error is bounded above by b sub n plus 1. That's the maximum our error is going to be. And we need our error to be less than 0.000005. All right. What is b sub n plus 1? Well, b sub n in an alternating series, b sub n is all the non-negative stuff. It's all this stuff that's non-alternating. That stuff right there is not b sub n plus 1, but it is b sub n. So we're going to plug in n plus 1 into this and find out what the solution to our inequality down below is. So plugging in n plus 1, we want, I have to zoom out to see it again, 0.3 raised to the 4. Normally I'd say n plus 3, but it's going to be n plus 1 plus 3 over 4 times n plus 1 plus 3. And we want that to be less than 0.1, 2, 3, 4, 5, 6, and then the 5th digit. Now that you will not be able to solve by hand unless you happen to have learned Newton's method. But the reality is that would just be terrible to do via Newton's method as well. So you'll use technology for this, which is, it seems, I always hated this in any of my math classes when they would say, oh, well, now we're going to use technology. Well, if you allow me to use technology, then I'm just going to go ahead and use technology to approximate the integral from the beginning. But let's just do this. All right. So I'm going to share my screen on my desktop. There we go. And that should be shared now. All right. And what I'm going to do is go ahead and I want to find out when 0.3 raised to the 4n plus 7 is really what that comes out to be. So 4n plus 7. Oh, you know what? I'm going to say 4x because we're dealing with Desmos. 4x plus 7 divided by 4x plus 7. I want to know when that is less than 0.0000005. Better way to ask that is to say, if I subtract 0.1234565, when is that less than 0? I want to know when does that go negative, essentially. And in Desmos, you can kind of do this pretty quickly. Oh, by the way, let me put this as y equals just so I can, I don't know why, it's just I wanted to. Desmos, you can kind of do that quickly. Well, times 0, it's 0. I saw another dot on there. Give me a moment right there. Desmos has a hard time with really like finite or infinitesimal calculations. I'm going to say basically from n equals 0.8, but I'm not sure. So let me see if I have it over here, because sometimes sometimes I have that. So let's see. Really, really hard. Let me see if I zoom in enough. Will it? Okay. All right. So I happen to know that it's less than 0 at 1.9. Let me go ahead and scroll back a little bit further. It looks like it's less than 0 for all that time. So let me just make sure that after, I should just, you know what I should do? I should just change the y-axis values to be from 0.02 to 0.002. That might be a little bit cleaner. Who knows? And then it's going to take all day, so I'm just going to zoom out. Okay, I'm going to zoom in as much as I can right here, because this is where the where it went negative. Okay, so you can see it's positive in this region, right? But it's going to go negative pretty soon. I'm just going to scroll over a few units. I think it goes negative somewhere around here. Sorry, it takes so long on this. Huh. Can't find it. Oh, there it is. 0.78. I'm going to try to keep focused on that. All right, finally. After 0.78, it goes negative. Man, that took a while to get there, didn't it? All right. So after 0.78, it goes negative. So, and that's what I wanted. I'll showcase why when I get back to my main screen here. There we go. All right. So all I did there was take this statement right here. I subtracted 0.00005 from both sides to get this. I want to know when is that less than 0, and that implies that n has to be greater than roughly 0.78. Now remember, I'm sorry, that n has to be greater than 0.78. Now remember that n is a number, so it has to be greater than or equal to 1. When I say a number, it's a natural number. So it has to be greater than or equal to 1. So to get that level of accuracy, actually, all we'd have to do is add up to n equals 1 from 0 to 1. That's it. So if I do that for 6 decimal places of accuracy, I will get the integral from 0 to 0.3 of our original function, which is x squared over 1 plus x to the fourth dx. It's approximately equal to the summation n equals 0 to 1. Very quick, right? 0 to 1 of, let's see, a negative 1 to the nth, 0.3 to the 4n plus 3. Over 4n plus 3. All right. So adding up that many terms, the first 2 terms technically, because it starts at 0, will give us that level of accuracy. And you can grab a calculator for that if you want to. So not too bad. I know that's a big example, but it really does showcase that table that I'm using, that it does kind of work nicely with the table. It is a bear, don't get me wrong. It's a bit of a mess, but there you have it. Little extra theorems that we have in here. So one thing that you should note when you go through is there are going to be some power series that are just very important to remember. And this is one of those power series. The natural log of 1 plus x equaling the summation n equals 1 to infinity of negative 1 to the n minus 1 x to the nth over n, where the radius of convergence is 1, or in other words, interval of convergence is negative 1 to 1. This is something that you probably should commit to memory. How would you prove something like this? We'll do it very quickly because we just have 3 minutes. We have our function versus power series world. I'll draw my 3 lines. I really like this, so I'm just going to do that now. Our function that we were given is the natural log of 1 plus x. Our goal is to arrive, so we're going to start there. Our goal is to arrive at the power series version of that. So we want to end at the power series version of that. Well, right now, just going directly over there, this direction, no. There's just no way you can do it. So now you have to ask yourself, do you want to integrate or do you want to differentiate? What do you want to do? Integrate or differentiate? You better believe differentiate. So I'm going to write this as hard, and I'm going to write the hard. I'm going to write the other one as easy because I can easily differentiate that. That's going to be black ink, f prime. This is going to be 1 over 1 plus x. And now you can see writing the power series for that is going to be super duper nice, right? That's also pretty easy. That's 1 over 1 minus a negative x, or in other words, the summation n equals 0 to infinity of negative x. Darn it. Negative x to the n. A better way of writing that, by the way, is summation n equals 0 to infinity of negative 1 to the nth x to the nth. Well, we differentiated to get there, so we'll have to integrate to get up 1 level, right? So this is going to be, let's see if that's actually right. I feel as though there's something. No, that's right. That's right. Yeah, that is absolutely right. Okay, so we're going to integrate this. Now, the integral of this to get up is actually pretty easy as well. Now, what you're going to see when we finish this out is that it's not exactly, doesn't look the same, but it is the same. So summation n equals 0 to infinity, -1 to the nth x to the n dx. We're almost done, don't worry. Integrating, you get c plus, and now remember, you don't change your index here. It's n equals 0 to infinity. That -1 to the nth, it's just a constant. We'll add 1 power to x and divide by the new power. And that should be the natural log of 1 plus x. Here's the trick. If x equals 0, we have the natural log of 1 is equal to c plus this stuff. This allows us to find out what c is. If x were 0, you'd have that. Natural log of 1 is 0. This is 0, and so we get that 0 must equal c. So we get that this is going to be the summation n equals 0 to infinity, -1 to the nth, x to the n plus 1 over n plus 1. And you say, wait a second, that's not what they have up there. It is actually what they have up there. It's just a different form of it. But if you let n equal 0, you will get 1 in the denominator, 1 in the exponent. If you let n equal 1, you get 1 in the denominator, 1 in the exponent. If you let n equal 2, you'll get, if you go over here and you let n equal 1, you get 2 in the denominator, 2 in the exponent. If you let n equal the second term here, which would be n equals 2, you get 2 in the denominator and 2 in the exponent. These are actually the same power series. No, there weren't any problems where I used all 3 rows, but in my video lecture, I'm going to redo it so that I can do this, so that you can see there is one problem that will use all 3 rows in the video lecture. There's just 2 problems in the video lecture. Anyway, I kept you guys way too long. I'm so sorry, but it was just something to get through. So, all right. I will see you guys either in office hours in 7 minutes, or sometime during the day, because you have a quiz today, or on Wednesday. All right. You guys have a wonderful, wonderful day. And I'm going to quickly, between sets here, go ahead and put in all the information for the quiz. Let me just say it out loud right now so that you guys have the information for your own knowledge base here. Let's see. The quiz is on 11.5, and I'm in student view. Give me a moment. There we go. 11.5, and it is 12 minutes, 2 questions. 12 minutes and 2 questions. All right. Have a great day. Have a good one. Bye-bye.